This video focuses on stereotopicity and the consequences of stereotopic relationships for chemical equivalence and chemical non-equivalence, as well as proton-proton spin-spin coupling. Compounds such as dichloromethane have homotopic atoms. Even if we substitute one of the hydrogens with some other atom, we have not generated a chiral compound, since the two chlorines are identical. NMR spectroscopy does not distinguish between homotopic atoms. For a compound such as propanoic acid, the methylene hydrogen atoms are enantiotopic. Changing one of the hydrogen atoms to another group creates a chiral center. However, the enantiomers are not distinguishable by NMR spectroscopy. However, in the case of 3-hydroxybutanoic acid, which now contains a chiral center, the hydrogens at the methylene group are diastereotopic. Changing different hydrogens will create a second chiral center in the molecule, and the two compounds that can be formed are diastereomers. In NMR spectroscopy, even the two hydrogen atoms are chemically non-equivalent when they are diastereotopic. And we'll see some examples of this in the slides to come. For carboxylic amides, the substituents on the nitrogen are diastereotopic at room temperature due to a very slow rate of rotation around the carbonyl carbon to nitrogen bond. As a result, the methyl groups in this structure are diastereotopic and exhibit slightly different chemical shifts as they are chemically non-equivalent. So the appearance of an apparent doublet is misleading. These are actually two singlets with similar but non-equivalent resonance frequencies. In principle, the individual hydrogens on a methyl group that is attached to a chiral center are diastereotopic. But in a practical sense, because of the very low barrier to rotation about the carbon-carbon bond, therefore, the protons on the methyl group are effectively homotopic and give a single resonance. This is an example of a symmetrical top, which also includes tertiary butyl groups and trimethylsilyl substituents. For a 1,2-disubstituted ethane derivative, where the substituents are not identical, the hydrogens are enantiotopic in the antiperiplanar conformer, but are diastereotopic in any other staggered conformer, including both of the synclinal conformers shown. The textbook does not mention this, but for 1,2-dihalogen compounds, the conformers with the halogens gauche to each other are preferred in the equilibrium relative to the halogens in an antiperiplanar conformer. Specifically, the synclinal conformers are enantiomers. If we now add another substituent that makes this into a chiral compound, now the methylene hydrogens are diastereotopic in all conformations. I'll show two proton NMR spectra that exemplifies this. The first being 1-chloro-1-iodoethane, which is a chiral compound, but because of the low barrier to rotation around the carbon-carbon bond, the methyl group is a single resonance as a result of being able to spin as a symmetrical top. We see the expected collection of frequencies. We have the quartet for the hydrogen at 5.9 ppm, and then a single resonance for the methyl group, which is a doublet at 2.4 to 2.5 ppm. If we examine 1-bromo-2-chloroethane, we now see a spectrum that is not first order, and there are a couple of complications. First of all, the difference in frequencies over the coupling constant is much lower than 8. In addition, the anti-periplanar conformer that is shown is probably a minor conformer relative to the chiral synclinal conformers. Therefore, the spin-spin couplings are virtually impossible to analyze. In aromatic compounds, it is not unusual to find that protons that are chemically equivalent are magnetically non-equivalent. And this results in non-first order spectra. The way that I think about this is that the hydrogen at A has 3-bond coupling with the orthohydrogen X and a 5-bond coupling of smaller magnitude with the para-hydrogen X. We see the same behavior with symmetrically 1,2 disubstituted aromatic compounds, such as 1,2-dichlorobenzene. We revisit the spectra of styrene, where we had previously worked through the alkene hydrogen assignments. For the aromatic ring, we see a non-first order spectrum for the peaks that are ortho and meta to the alkene substituent. However, the hydrogen C that is para to the alkene substituent has first order coupling, and it is a triplet of triplets, more easily viewed by a list of frequencies, which I found on a website, albeit at a different magnetic field strength. This slide shows the spectrum of 1-hexanol. This spectrum is integrated, and so this actually provides a lot of additional information. What is shown at the top is Popel notation, and for the alkyl groups that are distant from the hydroxyl group, A, B, C, and D represent chemical shifts that are close together. When labeling spectra, particularly for unknown compounds, I prefer to use lowercase Roman letters for proton spectra and capital Roman letters for carbon-13 spectra, as we will see later. I find it's easier to keep track if I label these. So at 3.6 we have 2 hydrogens. So this is downfield. I start out with A. Then we have a 1H hydrogen that is B, 2H hydrogen, that is C, and then we see several multiplets together. That totals 6 hydrogens. Since we actually know the structure, I'll label these D2, E2, and F2 because at high enough field strength, in principle, these can be separated. And then the methyl group, which integrates to 3 hydrogens, I'll call that lowercase g3. We can now assign the peaks to individual methylene groups. At 3.6, A2 corresponds to a methylene group that is bonded to an electronegative oxygen and is adjacent to another methylene. Therefore, this is a triplet. The signal at 2.2 parts per million, which integrates to 1H, is the hydroxyl hydrogen, B. And then C2 corresponds, C2 at about 1.5 parts per million corresponds to the second methylene group. It is an apparent pentet, but it actually is the consequence of 2 triplets with the adjacent methylene groups. We can't easily analyze D, E, and F. However, we know that the methyl group is at the terminus, and so this is G3, and the triplet is consistent with it being bonded to a methylene group. We can make an educated guess that these methylene groups follow in order with increasing distance from the electronegative hydroxyl group. But this is actually a guess with fairly high but not 100% confidence. This healthy skepticism will become important with more complex structures. This is a proton NMR spectrum of 3-methyl glutaric acid. The spectrum is quite complex. However, 3-methyl glutaric acid is an achiral compound. But the complexity of the spectrum arises in part from there being homotopic groups, enantiotopic groups, and diastereotopic atoms. We'll return to the spectrum after we consider the stereotopicity. The methyl group and the adjacent hydrogen labeled hydrogen C are homotopic. The methyl group is a homotopic group. Hydrogen C is a homotopic atom. Changing either of these groups does not generate a chiral compound. For the methylene hydrogens, the individual hydrogens are diastereotopic. Changing one of the hydrogens to another group now creates 2 chiral centers at carbons 2 and 3. The carboxylic acids are enantiotopic. If one of the carboxylic acids is selectively changed into something else, and enzymes are actually quite good at doing this by selective acylations, then carbon 3 becomes a chiral center. Now let's return to the proton NMR spectrum. The textbook specified that the solvent for this spectrum is D2O. Therefore, the carboxylic acids are actually now deuterated, and therefore there is not a proton for the carboxylic acid, which simplifies the analysis. If we label the resonances A2 for 2 hydrogens, the next multiplet integrates to 1 hydrogen, and then the final multiplet integrates to 2 hydrogens. And there is some overlap between B and C2. The methyl group is D3. This is slightly different from the Popel notation. As we analyze this, hopefully we can now see that the doublet of doublets, and here's another doublet of doublets, correspond to the methylene hydrogens that are diastereotopic. I don't think that we can specifically assign whether A is the pro-R or the pro-S hydrogen. However, we can assign B to the methine hydrogen attached to carbon 3. And then the methyl doublet, as expected, is D3. Because of overlap, we can't see the full coupling pattern for B, but we expect it to be a triplet of quartets. Figure 3.42 depicts the NMR spectrum of ipsenol. We will return to this spectrum a couple of more times as the course progresses. It is introduced here for the first time. I will label the proton spectra at the bottom. So there is a peak at 6.4, which is a single hydrogen. Then there are 4 hydrogens between 5.5 and 5.0 parts per million. And I will label these B, C, D, and E, because from the structure I know that they will be chemically non-equivalent. At 3.8, there is a 1H hydrogen. At 2.5, another 1H hydrogen. At 2.2, a 1H hydrogen. These two look like they might be diastereotopic on a methylene, but that remains to be proven. And with 2D spectroscopy, we will be able to show how we can prove that without making what is currently an educated guess. At 1.8, this integrates to 2, but notice that there is some breadth, and from infrared spectroscopy, we know that there is an alcohol, so I will call these by 2 different letters, I and J, one of them being the hydroxyl OH. And then 1.5, we have K and L, and because of the way these lean toward each other, these look like they may be another diastereotopic pair. That is an educated guess that will be proven more conclusively with 2-dimensional NMR later in the semester. At 0.9 parts per million, there is an apparent triplet that integrates to 6 hydrogens. But at higher field strength, we can see that there are actually 4 signals, and that corresponds to 2 doublets. This is also demonstrated by changing the solvent from deuteriochloroform to deuteriobenzene. Deuteriobenzene is a more shielding solvent, but the peaks often will not shift by exactly the same amount. Whenever you have overlapping peaks, I recommend taking another spectrum in a different deuterated solvent. I will label the 2 doublets M3 and N3. I'll point out in the 600 megahertz spectrum that we can now see the 4 protons that are B, C, D, E, So this is now B, which is a doublet with a large coupling constant. This is C, which is a multiplet with very small coupling constants. This is D, which is two multiplets with the largest coupling constant, but it's smaller than what we saw for B. And then E is another broad peak. The spectrum at 600 megahertz is well resolved, whereas the corresponding spectrum at 300 megahertz shows overlap between D and E. I will now propose specific assignments, although these will be checked later in the semester with data from various two-dimensional NMR experiments. The doublet of doublets at 6.4 parts per million corresponds to the methine CH, which is labeled carbon 7. B, with a large coupling constant, is the trans hydrogen at H8. C is one of the hydrogens at C10. D is the cis hydrogen at H8. And E is the other hydrogen at C10. F, with a chemical shift of 3.8, is consistent with a carbonyl hydrogen, which is at C4. G and H are downfield enough to where I suspect that they are allylic hydrogens at C5, with the chiral center next door at C4. These hydrogens are diastereotopic. I and J are the OH and the methine hydrogen at C2. K and L are the other diastereotopic hydrogens on methylene carbon 3. And then M3 and N3 are the diastereotopic methyls 1 and 9, although we cannot specifically assign which diastereotopic methyl is M3 versus N3. This is the NMR spectrum of 3-butyne-1-ol. I'll start out by labeling the peaks. So the one that is listed as carbon 1, if there was an integral, that should integrate to 2 hydrogens, so I will call that A2. The peak at 2.4, which looks like a doublet of triplets, should also integrate to 2 hydrogens. Then there's a peak labeled as the OH peak, which is 1H, I'll label that C, and the terminal alkyne hydrogen, which is at 4, is a triplet, and I will label that as D. The selective proton-proton spin decoupling experiment is not that widely used any longer. However, you can see how irradiation simplifies the coupling patterns and shows which protons are affected by coupling with other proton nuclei. What I want to point out in particular is that there is a 4-bond coupling between the hydrogens at carbon 2 and carbon 4. This is not unusual for alkynes due to the rigidity of the carbon-carbon triple bond. We can also see this with the list of frequencies which I took from a website which provided 400 megahertz couplings. We see the triplet for A2 with coupling constants of about 6.5 hertz. In the other spectrum, which was more concentrated, the hydroxyl group was downfield due to more hydrogen bonding at 3.478 parts per million. For B2, the frequency lines show 6 peaks. There's one line that is noise. This is revealed as a doublet of triplets, and I've given the coupling in order of the corresponding coupling constant. Finally, we see a triplet. The chemical shift is slightly different, but you can clearly see the 1:2:1 relative integration, and the coupling constants for D are on the order of 2.7 hertz. And this again is consistent with a 4-bond coupling constant. This chapter concludes with a brief discussion of through-space nuclear Overhauser enhancement experiments. We will revisit this later with proton-proton nuclear Overhauser enhancement correlation spectroscopy, but I will briefly show how we can assign the methyl groups correlating with the assigned hydrogens. The hydrogen at C6 is assigned as being downfield due to its bonding with the oxygen of the pyrone ring, with H4 being the other alkene singlet. What is not immediately obvious is for the two methyl groups, what the methyl group at 1.9 is attached relative to the methyl group at 1.3 parts per million. This is where the NOE difference experiment is valuable. Upon irradiation of the 1.3 parts per million methyl group, we see nuclear Overhauser enhancement of both of the alkene hydrogens. And that is consistent with the methyl group being attached to carbon 5 in proximity to the hydrogen bonded to carbon 4 and the hydrogen bonded to carbon 6. As a control experiment, we can then irradiate the remaining methyl group at 1.9 parts per million, and we see an enhancement only for the H4 hydrogen and no enhancement for H6. That is consistent with the methyl group being attached to carbon 3, close to the hydrogen at carbon 4, but distant from the hydrogen at carbon 6.